Welcome to this introduction into hydrogeology as it relates to geological waste repository. So my name is Massimo Rossini. I'm with the SKB, working at the SH262V Hard Rock Laboratory as a hydrogeologist for some years now. And the idea with this lecture is first and foremost to give you some basic introduction into hydrogeology. I don't know your background. Some are very knowledgeable, probably, and some less knowledgeable. So I've tried to keep a level which is accommodating most of you. The lectures today consist of 2 lectures. Vaclav said it's 3. There is one tomorrow. The first 2 is basics, where I want to introduce you into the context of hydrogeology, definitions, concepts. Also, the basic tools which we have to do measurements and what we do with the data, basically, to produce a model. Later on, I will give you an example in the second lecture of a project where I go through the whole steps from the beginning until the end. That's the framework of these 2 lectures. So, what is hydrogeology? Very simple. It's to study groundwater and its applications. And we have 2 branches, basically. One is the scientific part, to understand the groundwater and its couplings in the whole terrestrial systems. And the other one is the engineering, which is supposed to support the development in society. SKB has done a lot of scientific research in this context. A lot has been done at the SH262V Hard Rock Laboratory, but also elsewhere within the academic community. Some examples of these 2 applications in science: we have well testing, the first one, where a borehole is basically our window into the rock, from which we extract direct data, which then is processed further. I will go through some of those steps. Monitoring is basically time series, which is also being researched upon. Discharge is a never-ending issue. You can always learn more. And then those two last parts are those where SKB has done most of its research in flow in heterogeneous systems and in homogenization. Homogenization meaning go from a heterogeneous reality to some kind of homogeneous average. That was the science. In engineering, it is groundwater assessment. This is particularly important in arid and semi-arid countries, but it's done everywhere, of course. We have groundwater contamination and remediation, which is where this waste repository issue belongs. Saltwater intrusion in all coastal areas, and also when we have upconing, when we have a tunnel or a cave, basically. Tunnel inflow, very important. The crucial issue is water and the rock stability there. And then mine dewatering. You have to keep the mine dry in order to operate there. Basics. So the relevance of hydrogeology to the geological storage. We have 3 legs which we are standing on. The first one is the site selection. So we have to find a site which is suitable. What is suitable? That depends on the country. But that is one part. The second one is constructability. Once we have found the site and we have to go down there, we must make sure that we can construct. The conditions are right, or else that we make them right. And the third one is the crucial one in this context, and that is to sort out travel paths and travel time in case there is a leakage. Meaning basically this picture here. So we have a canister. So if we have a leak, where does it go? When does it go there? How much? And this is relating directly to the safety. to the safety assessment and the risk assessment. So the whole geological storage issue is basically to make the case credible that we can accommodate this storage under this risk criterion, which is that the annual risk of harmful effects must not exceed 10 to the minus 6 for a representative individual in the group exposed to the greatest risk. So this is nothing which I as a hydrogeologist deal with directly, but I want to show you that this hydrogeological component is an input towards this end, where there are also several other components in other disciplines. So we go from investigation into some kind of understanding, and this is showing the basic steps which we do have. The investigation, of course, there is a lot of input to make a program and to perform them, of course. The other part is the database and the quality assurance and quality control system on what we have produced in terms of data and on how we have evaluated it and utilized it. Then it goes to interpretation of geometries and properties, general. And the central part here is the geologist, the structural geologist, around which all the other disciplines which you see, these disciplines mentioned here, of course. That is the common structural framework, the geometric framework, I would like to say. So each discipline produces a site descriptive model by its own rights. And this is an integrated, interdisciplinary, consistent description, consistent between the disciplines, based on fundamental understanding of rock and surface system, including geometries, properties, and processes. That's the condensed version. And this results in a site description. A site description is a report where all these models are discussed. So I brought one here just to show you. For the ones who want to browse it, you're welcome. You can pass it on if you like, just to give you an idea. So this is all the disciplines. So we are going towards that site description, but I will step you through from the beginning, from the investigations. That was the wrong. So the repository is supposed to be placed down here, okay, in the ground, and this is part of the hydrologic cycle and the terrestrial cycle, the lithological one. So this shows in terms of water what kind of input-output we have, and as a hydrogeologist, which is the water part very much, is to address all these transport and venues of the water. Once the water gets down in the ground from precipitation, we define three basic units in terms of an aquifer, which is the part which is more conductive of water. And the definition of an aquifer is that if I put a borehole in the ground, I will be able to pump out water. If I cannot do that in terms of reasonable quantities, then it is not defined. That's the simple definition of aquifer. And then we have the other two units, which is an aquiclude, which is releasing water but very slowly, and then the aquitard, which is considered impermeable. But of course nothing is impermeable in sensu stricto, but the aquitard is normally at the bottom of the aquiclude system, as an aquiclude is, for example, a clay layer or any other geological unit with less permeable properties. We also have, of course, the groundwater table in the upper part of the aquifer, which is up here. Okay, this is in contact with atmospheric pressure and is defined as an unconfined aquifer. And then we have a confined aquifer, which is an aquifer which is under pressure. So it's like a lid. From recharge to discharge. So these are the basic components of the actual transport system, where we have groundwater recharge. Of course, the basic recharge comes from precipitation in somehow, directly through infiltration, percolation, or through some kind of water surface body, a lake or a creek or something. Going down through the unsaturated zone and then down to the aquifer, which is defined as the saturated part of the ground, and producing a recharge of water. And then we also have a through flow, of course. It can be slow, it can be quick. And the other component here is the evaporation, that it takes up, it can be quite a lot, the water which is go through the vegetation system. This is a couple of examples of recharge and discharge. The left picture shows a time series where precipitation events are plotted with the water level at different depths in the ground. So this is the biggest precipitation event here, if we look at this, for example. So we can see that the red, the green, and the pink curves here responds clearly here for these precipitation events with a rise in water table, or pressure rather. It's the same also for the creek. Water is contributed through the precipitation, so this is recharge events. And what we can also see here is that all precipitation events do not produce a recharge. It depends on the condition, the initial condition of the aquifer and of the unsaturated zone, how much water has to be accumulated before it can be transmitted, and of course on the precipitation events. The other thing we can see from this picture is that the deep aquifer has a higher pressure than the shallow aquifers, which means that there is a pressure from below pushing up, which is what we call a discharge area. So we have recharge, and it is a discharge area in this case. The other example is for a discharge event in terms of the evapotranspiration, which I showed previously, where we have the black line. Again, it's the water level. So we have a general declining water level because it is summer, and we have in additional here, incremental, additional decrease in water level during the day when we have the actual potential, the evapotranspiration, sorry. So these are two examples. Recharge, discharge. Now, the groundwater reservoir, it's either crystalline, that is magmatic rock from the lava, okay, in different kinds of lavas, which is cooled, solidified, and it creates, you know, rock like granites, for example. The other one is sedimentary rocks, which are, it's weathered magmatic rock, which first produces soils and then through compaction and high temperatures and chemical solidification becomes a kind of sedimentary rock of different kind, like a sandstone, for example. Then we also distinguish between porosity. Primary porosity is the porosity between the granular, the grains basically, and then secondary porosity, which is fracturing, which is come at a later stage. Okay, the soils which are granular, of course, we distinguish between well sorted and poorly sorted. Very evident. And there are also soils which have porous pebbles as such. It's not common, but it exists. Then, of course, we have the sedimentary rock, which I mentioned This one, and the other one is a sedimentary rock which has been chemically weathered, creating large fractures, even caverns. It's called karstic terrains. And the last one here is the fractured rock, F, which is what we're dealing with here at Esbjerg in Sweden, a granitic environment. Now, when the water comes into the ground, it flows away, and we have different, which is important to understand the system here, and this is actually important because it's a very good coupling between chemistry and hydrology here, where the water has a certain composition. The precipitated water, which is very diluted, enters the ground and picks up solutes, ions, and changes composition. So depending on how long time it stays in the ground, and of course on the properties of a rock, you will get different compositions on the groundwater. So we need to be able to establish the age of the water from days to millennia and even millions of years, as the case is at Esbjerg, where the oldest water is millions of years. In order to get this age of the water, of course we need a water sample, but then it's radioisotopes are utilized to this effect, and we have different isotopes depending on how old the water is. And the oldest waters are dated with chlorine 36 and krypton 81. At Esbjerg we use chlorine 36. The driving force, when the water gets into the ground and then flows away, you need some kind of force, and this is basically the difference in groundwater level. Or if it is confined, it's a groundwater head, which is what this picture wants to show you. So we have a ground level here. This is the borehole, and if we have an intake here in the well, at this point we want to measure the head here, or the pressure. So we measure actually the pressure, okay, with the pressure transducer. We obtain a head which consists of the actual water column above the groundwater, the pressure transducer, and it's all related to a certain datum. Normally the water, not the water, the sea level. So this means that the head, the hydraulic head, is the component, the pressure head from the column above the transducer, and you add the elevation head, which gives the hydraulic head. That's the driving force. So this is an example of an installation which is standard. So we have a borehole which have been sealed off with two packers. So we have 3 sections, and measuring pressure in each section. And for example results here are that we have 3 time series with 3 different pressures. So the first section, or the deepest section, represents the uppermost curve, which consequently has the highest head. And then you have a lower in the middle section, and the lowest head is in the uppermost section. And this means, again, sorry, wrong side, again, that this shows that we have a force pushing water up a discharge area. This example is taken from Esbjerg. And so that is in one borehole. Now we have different boreholes. So with that we can tie these different heads together and produce a map with same potential for a certain level. So this wants to represent, this is measurements done at the Esbjerg laboratory, where we have quite a lot of measurements done continuously, which shows the groundwater head at 400 meter level, so at 400 meter depth. And what we can see from here, that this is a code of depression, the most low-lying pressures. We have a groundwater which is approximately 300 to 350 meters below ground, below mean sea level. And this type of information is used to deduct where does a certain particle which is released from one point in the canister, where does it go? So this is fundamental information which is needed as an input. Then there is a relationship between the amount of flow through the ground and the hydraulic gradient, which was just established some years ago, which is basically an analogy to this. There are analogous laws in electronics, in the diffusion equation, fix, and so on. So the flow is the flow through a certain cross-sectional area is the conductivity of the rock multiplied by hydraulic gradient for that cross-sectional area. So for a well, for example, we measure the groundwater level in two different wells and calculate the difference, and we have the distance, the difference in distance, of course, to obtain the hydraulic gradient. And the cross-sectional area is the diameter of the well, and the hydraulic conductivity is something which has to be calculated. Unless you can measure the flow, like it was done in a laboratory to establish this law. It's called Darcy's law. There are limitations to Darcy's law, which are important to know about. So this is a microscopic. That is, when we look at a certain particle in the water, which is flowing through the system, it has a very tortuous path, represented by this blue line. Real path, real velocities. But Darcy's law looks at averaged paths, averaged velocities, which are the ones that are measured. We cannot measure at that very, very small scale. So at a macroscopic scale, it is applicable. If we go and look closer and closer at microscopic scale, it is not valid. The other case where it is not valid is when we have a turbulent flow. So if the velocity is too high, then we have got vortices and laminar flow doesn't exist. And again, Darcy's law is not valid in those cases. And this happens the turbulent flow can occur in karstic rock, which I mentioned previously, and cavernous volcanics, and also in fractures of wide aperture. This is the standard interpretation. Of course, it is also possible that we can have turbulent flow at low velocities. So to summarize the hydraulic conductivity, it's a proportionality constant derived from Darcy's law. Okay, we know now it's a representative property of the aquifer, of the conductive property of the aquifer. It is very variable in nature. It is log normally distributed in space. That is proven empirically. And then it is usually measured with the pumping test, which is a standard easy test to perform. So the hydraulic conductivity has a very wide range. So this is the top. These are soils, different type of soils, sedimentary rock and crystalline rock of different kinds. So what this wants to show you is that in all type of geologic material, we have this wide range. And the range is from around minus 13, minus 14 meter per second to 10 to minus 2. And we have measured 10 to minus 13 on cores from outside of Esbø. But the highest we have measured at Esbø is around minus 5, minus 4. Just to give you an So if we look at, that was generally speaking in geological materials. If we look at crystalline rock in Sweden, then we have this distribution, which shows the hydraulic conductivity. So the cumulative curve for different investigations that SKB has conducted. What we can see is that for Forsmark, which is the site for the repository, we have this curve here. Basically, we have some kind of average conductivity of -11, and that is also very homogeneous in that respect. It's not so poorly distributed. While on the other hand, if we look at this curve, which is the other extreme, which is an example taken from Laxemar, which is outside of Espö, which was the other candidate site when we did the site investigations for the geological repository. We have this curve here. You see that you have a much wider spread, and of course also the average is around here, -10. Yes?
Is that just because of more fractures?
Yeah, it is. It is rather common. The anomaly is not so much. Yeah, it is more fractures. Yeah, let's not go into that. Yeah. Okay. So now I've been talking about conductivity, how transmissive the rock is for water. The other important parameter as a property of the aquifer is the storage coefficient. How much water can the rock store? And basically there are two types of storages. One is the specific yield, which is in the unconfined aquifer, which is basically the pore volume which is available, accessible to be drained. So the standard, or rather the definition for the specific yield, is that if we take a unit area and we take a unit decline in head, then how much water is being drained relative to the total volume from which it's being drained. Very straightforward. That is the storage for the gravity drainage. The other type of storage is through compression, and that is the situation in the confined aquifer, which I mentioned previously, where here we have the confining layer down here, and we have two boreholes open in this lower aquifer. So this is an upper aquifer and this is a lower aquifer, and they are isolated between each other through this confining layer. So this means that it is under pressure, and we will have, when we insert a borehole, we will have a pressure rise up to this level. Okay. For a unit decline in head, the definition is the same here. Okay. And for a unit area, then we have the process of aquifer compaction. Of course, you release the pressure, the aquifer is compacting, and at the same time the water is expanding. Usually water is classified as incompressible or almost incompressible, but in this case, depending on the properties of a rock, it can be important. And I have a graph here so this is basically those two. So this shows exactly this, the compressibility of water and aquifer, in relation to the compressibility of water. So down here is the water's compressibility. This is square meters per Newton. Okay, so we see that fissured rock has a compressibility with water, of course, the aquifer, fissured rock aquifer, which is in the range of the compressibility of water. And if we have good rock, which is what we are targeted for the geological repository, then it is even lower. So all of a sudden, well, not so sudden, but in these cases, the compressibility of water is important to take into consideration. Okay, now just give you some ranges of this storage. For the unconfined case, that is when it is open to the aquifer, we have, this is a percentage basically, because it was drain volume related to total volume. Oops, not again. So depending on the grain size and the rock, it varies from a few percent up to 30–40%. That's the normal for the specific yield. For the storage coefficient, then I've taken examples from crystalline rock, which we have measured at SPE, where it varies. So it's this scale here you should look at. So it's 10 to the minus 3 or 10 to the minus 4 to 10 to the minus 6. That is for that system. Now, so those were the relations for groundwater transmissive properties and for storage. Another very, very important issue in terms of understanding the system is how heterogeneous and how homogeneous it is, because all theories in terms of understanding the relation between a certain input and another output in the system is based on very simple conditions: homogeneous system, infinite, and so on. The reality is that it's very heterogeneous and that we have dependencies in terms of directional dependencies, depth layering or fracturing, which is called it is anisotropy, and then we have a heterogeneity, which means that it is spatially dependent. So if we focus on these two, this picture is trying to explain these two issues. So we can have systems that aquifers that are homogeneous and isotropic to heterogeneous and anisotropic. So an homogeneous isotropic means that for a certain at a certain point in the aquifer, the magnitude of the property is the same in all directions. Okay, the vector is equally long. And if I go to another point in that aquifer, it has the same size as at the other point. That is homogeneous and isotropic. And the other end is, of course, the opposite. I mean, they are different in different directions, and if I go to another place, they are different in a totally different way. Was that confusing? No. Okay. The third point here is scale dependence and support volume. So when we make measurements for a certain property, like a storativity or a hydraulic conductivity, then we do the measurement with a certain equipment, with a certain length scale. And it is absolutely crucial that we are aware of the scale at which the measurement is made, because then when we use the data, usually we don't use it at that scale. We discretize our world, the 3D world, into cubes, which are much larger. So there is a scale dependency. So if I measure at this scale, I won't get the same answer as if I measure at this scale for the same borehole. So this is an important issue which is being dealt with. And of course, that the scale dependency is directly related to the support volume, which is basically the volume of the rock which is supporting, affecting the measurement. Scale dependence. So this is an example. Measurements at different scales. The x-axis, this is meters, logged meters. So we have from a few this one, from a few half a meter here to 1 kilometer long borehole. So we have a greater variability with smaller scale. It's quite natural, and also we see that it converges for that rock. This is SPE, converges towards some kind of global not equilibrium average. These are that is one component. Then what hydrogeologists also do is that we try to find relationship between fracture size and property correlations. This is important because it is utilized in the modeling. So this is one example of trying to find from actual measured data. This is length and transmissivity for different projects. So how we can try to find a certain trend or correlation. Similar here, another important issue which I'm not going to discuss, but just mention, is the aperture, the fracture, the aperture of a fracture, which is transporting the solutes. Also correlated. And the third one is the storage. The storage correlation with the hydraulic conductivity. So with these correlations, we end up with some kind of, I mean, one can do different type of correlation equations. These are all power law type. And these are utilized for assigning properties to fractures generated by the numerical model. And then they are producing fractures to adhere to a certain statistics which we see when we do measurement on fractures, which is done by the geologists. I think he will mention it. Spatial, okay, so this is basically what I have mentioned, just examples. We have the depth anisotropy, so we have a decreasing conductivity with increasing depth. Depending on fracturing, we can see that the open fractures, the central picture here, this is the direction of the open fracture. So this, in this case, the north-south trending fractures are conducting water very well, and in the other direction, they are not conducting water so well. And then the third example is heterogeneity. So we have in one and the same borehole here, you see it varies 1, 2, 3, 4 orders of magnitude. And this scale, I should have mentioned it, but this is measured at 1 meter scale. And in order to arrive at this parameters, torrativity, conductivity, and so on, we do 3 basic tests. The pumping test, which is basically perturbing, injecting or withdrawing water from one well and see what happens in terms of pressure or of water flow. The other one is that we measure between 2 points. If I disturb here, what happens there? And we obtain these type of parameters from these measurements. And then the third one is the flow logging. So we measure flow along the borehole and see how many conductive fractures do we have and how conductive are these fractures. Okay, so yeah, let's go take this one. So there is the most basic relationship between a pressure disturbance which one make in the aquifer system and the flow which is we are getting out of it is this relationship here, which is basically a relationship established for this geometry here. So we have an aquifer down here. The borehole is here pumping water. And what is important to know here is that this relationship is valid for homogeneous and isotropic aquifer. Okay, with constant thickness and infinite extent, which doesn't exist, you know, if you're really, really strict. But it has proven very, very, very useful, nevertheless, actually. So, but just to show you how we are going about is that once we do this pumping, we come up with a relationship. So this is pumping time, and the green line is the pressure difference from time 0 and its derivative, basically. So from the shape of this curve, okay, we can derive the unknown parameters here, and the unknown parameters are the properties of the aquifer, the storage coefficient and the transmissivity. All the other ones are known. Then there are complications to this because most often, or very often, the curve is not adhering to this theoretical curve. So it's much more complex, and one has to understand how. And there is a lot of research that has been done on that, and we have come a long way, and we can sort out most responses, but not all. Okay, any questions so far? Crystal clear. Yeah.
If I understood correctly, for your models, you're using a lot of like correlations.
Yeah.
Like so you take just some parameters, you take data, and then you, when you get some correlation, and it works probably for this type of rock in that area.
That's right. That's right.
You also do like modeling, like in continuum mechanics, like real modeling with I mean, so starting, I don't know, starting from balance equations and going through the whole modeling, like continuum mechanics. Do you
Yes, definitely. That is the basics.
Okay,
but this is not. I mean, modeling is done that way, based on continuum mechanics, and there is also the other component which is not continuous. It is that the fractures are discontinuous, and that is treated with stochastic what is it called, DFN models. Which I'm not covering modeling at all here, but that is quite right. It is based on those basic relations.
Okay.
Yeah. Okay, I think that I was planning to say something more about this, but it's time for a break. What do you think? Okay, let's take a break. Okay, welcome back from the break. One more slide from this, from the first lecture, basically, where I'm trying to tie up all this, the detailed fieldwork with what we're using it for in the end. So what we do have here is, what I've been trying to explain is how we go about. So let me explain the graph first. Okay, we have time here. Okay, so this is measurement time and time scales in general, and this is the y is the length or the scale. Okay, so when we do data collection and measurements, we are basically using a very narrow window in time from which we obtain our data. That is what we are basing our calculations on. The length scale of the tests, the data, is a little high. So we can go up to 1, 2, 3, 4 kilometers. Okay, but that is the confinement of the data. Then we do a model from the data, the site description, which this report was circulating, which is basically, you know, extending, but in length scale, we can look a little wider because we can model it a little wider. But yet again, the time window for which we do the modeling of a site description is for the time window basically from which we have the data. We need to calibrate. But then, so this is then the way we do data, geometry's properties, create a site description. Then the site description is utilized to make predictions on a much longer time scale and including scenarios of what will happen which will affect the system. And the basic thing is earthquakes, ice loads, okay, and the penetration of oxygen-rich water down to repository depth, which is a critical issue in terms of containing. So this is what it is being utilized in safety assessment, going to predictions. Okay, so this issue will be covered tomorrow by Patrik Widstrand. He is giving you a lecture on safety assessment. So that is done at much longer time scales and somewhat greater length scales. Then this are utilized to do the safety assessment, which is, we're going back to this criterion on the risk, you know, 10 to the minus 6 to the most exposed individual. So this is where the SKB makes the case towards the regulators that we think that this is safe because this and that and that and that. So of course we cannot prove anything in these time scales. So the question is to do perform things, you know, properly with quality and with good theories and get acceptance for it, that it sounds okay, and then make a case for which they have to judge, basically. Okay, that's no more. Now an example. Any questions about this last slide, by the way? So I will step you through here a project where we characterized and modeled for a tunnel called the ESP extension project, which is fairly recent. I will go through objectives, conceptualization, characterization, iterative approach up until the descriptive model for this very small volume, because the methodology is exactly the same, but of course the degree of ambition is different depending on the objective of the project. So the project, the idea here was we had to extend the tunnel by around 300 meters at 400 meters below ground level. And this was necessary because additional experiments needed to be performed, and we did not have suitable volumes for it, because we have a lot of experimental volumes, but they are occupied, they have disturbed, and so on and so on. So we had interested parties, stakeholders, who imposed certain conditions on us. One was that maintain high groundwater pressure. Okay. That was one condition. The other one was we should allow certain tunnels not to be grouted, because experiments they wanted to do concerned cement and so on. So if we grout it, then we disturb the site from the beginning. So we had to find the right spot. Then no subhorizontal permeable fracture planes to be allowed. And then, of course, the rock in general should be tied to intermediate to resemble the repository rock, which is up in. So in order to perform this project and to meet these objectives, the project was implemented with three sub-projects. The first one, characterization. Now look at the rock, what is it like? The second one, to design the tunnel, and the third one, to build it, to construct it. The geoscientific requirement here, this is basically covering what I have already mentioned, plus some additional requirements. Maximum tunnel inflow, 10 liters a minute, water salinity, 10 to 12, anoxic water condition, and then also undisturbed, so we shouldn't disturb. There are different, one big issue is that there are different experiments going on and they should not influence each other. So this takes great consideration when locating the site. So from desktop studies, we found a site which is basically in this part here, where we have yellow tunnels. And here we identify this volume, okay, around 300 by 300 meters cube. So what we did here was, first of all, do a site selection exercise. Is this site suitable? Can we move on after the initial assessment? If that is so, then we should characterize it more detailed. And with that as a base, we should design tunnels and then to build the tunnels. The starting point when going into this unknown volume is that what we want to do is that we want to conceptualize the very complex nature of the rock into something which is suitable to meet our demands, okay, and still which is suitable, you know, which is realistic to achieve. And to this end, we are dividing the volume into a rock volume which has tighter rock, and then which is cross-cut with more permeable fractures and fracture zones and deformation zones. That is the idea. And that then we have more saline water at the depth. This hydraulic soil up here was of no concern in ESPA. It's an old site, so that was not addressed at all. That was the conceptualization. So then, in order to meet the design demands and the criteria, and also in terms of high groundwater pressures, the whole project was established with a modeling exercise, basically, a characterization modeling. So the modeling objectives, or rather, first of all, the model is a simplification of reality, okay, where the level of simplification is chosen with respect to the issues or problems that need to be resolved. This is the general idea which one has to apply to each project. Then in this case it was a question of a deterministic discrete modeling approach. This means we have to find the fracture zones, we have to give them properties up down to a certain level, of course. So we can geometrically define, as I say, parameters, okay, of these zones. So in order, I mean, this was then utilized to select the site and confirm that it is okay, to in place the main tunnels, and to predict inflow and water and rock quality for the construction, and then to do the detailed layout and design in the end. That's what the modeling was feeding into. So the approach here from the beginning was, as I mentioned, we produced a desktop study with existing data. What do we have? What is our present understanding? With that, we made a very basic model. This is very simple, but still it's a model. Okay, so this is for site selection. So once we decided, and that is the cube I mentioned. So we identified the cube in the first step. Then the second step was to drill, to do pre-investigations. I will come to that, 2 boreholes and what we did. Okay, which produced yet another model. And this other model was supposed to confirm the site and to in place the tunnels, at least initially. Okay, once that was done, based on this model and the emplacement of the main tunnels, we drilled pilot holes along the direction of the intended tunnels to be characterized. And then collected data from this and then produced yet another model. Model number 2. Okay, so for model number 2, there were predictions, experimental tunnel emplacement. Okay, this was utilized. After this model, the final setting was made for the construction, and the tunnel was constructed, and during tunnel constructions there were several investigations undertaken. And then upon completion of tunnel, or rather during tunnel construction, we produced several sub-models, 2.x. So this, the objective with this model 2.x was predictions, experimental tunnels, not tunnel, and adjust and fine-tune the actual layout. How should we place the tunnels? Which one should be grouted? Which one should not be grouted? Where is the high pressure which they want? And so on. So these are the 2 first holes. After we have made the model M0, the 2 pre-investigation holes. So they were drilled. This is from a side view, one from the above floor, drilled downwards, and then the other one at the level of intended construction and drilled slightly downwards as well, going out sideways. Those were the 2 first holes. And for these 2 sites which produced, which gave data for the M1 model, we did this drilling inflows and head. This is the characterization which we did, which is fairly standard. So it's geology, geophysics in the borehole, and hydrology, hydrogeology basically, and also water sampling. But one thing which is important here is basically that the tunnel construction crew, they only want to know that if this salinity criteria is okay, if it is anoxic basically, then the site is okay. Then after that, they are not interested in chemistry, basically. So it had very little input, but we did a lot of chemistry anyway, because we ESPE as such. Now I'm talking about the project as such and ESPE as such. ESPE is a research facility. So we did a lot of chemistry just to build a better model. Okay, so at the end of this first model, we had this, the criteria which I mentioned previously. Okay, and then the outcome at that stage, the M1 model. So the pressure, this relates to the high groundwater pressures, okay, 390 meters, that's okay, promising. Tunnel inflow seems promising. how permeable is it? It looks okay. And salinity looks okay. Anoxic water, no results, so we don't know, but it's likely, and so on and so on. So based on this outcome, the go-ahead was given. Okay, let's construct. Let's do the pilot holes and construct. So these are the 2 pilot holes drilled, and some measurement sections. So we did the same, basically the same characterization for these pilot boreholes, okay, as for the site selection boreholes. Now, when we do the characterization, we want to know this following information. So the characterization shall give us the rock type, the fracture frequency. There are different types of fracture frequencies, and I mean open fractures, sealed fractures, conductive fractures, and also their geometry, because this is at the core of establishing the model and establishing this zone. So we always start at a small scale, because that is where we have a measurement. And then from that we have to extrapolate and sometimes interpolate. But usually it's extrapolation to tie things together and make a case that this is, you know, a 500-meter zone. So these were set. And from the tunnel construction, in terms of hydrogeology, we were not measuring. We were doing qualitative measurements of the water leakage. And that is, we were checking all over the place. Is it dripping? Is it wet, damp? Is it flowing? And basically we have three qualitative what is it called? Measures for the leakage. From the boreholes, what we wanted was very simple things. Transmissivity and storage. Transmissivity is basically, it's the conductivity which I mentioned previously multiplied by the length of a section. So it's the same thing almost. The storativity which I mentioned, the hydraulic conductivity, which I didn't go into, which is how connected is one spot with another one. So we produce response matrices there and then can construct a model. All this is compiled into a central database where we have the core of this handling is for the single hole interpretation. We have BoreMap WellCAD. These are tools producing logs basically in the database. And then the other one is a three-dimensional visualization system for the same. Now, when we do the hydraulic measurements, our standard setup in the borehole is a borehole with two packers where we define a test section which we want to test, and then we have a number of valves and transducers and measurements, you know, at the wellhead, and do measurements. So measurements is done, you know, at different sections, and we keep on moving around basically. That is for the type of test which is called pumping test or injection tests, not flow logging. Flow logging is a different. And this is a picture from installation of a packer system. This is the wellhead with all these valves and stuff. Now, when we have done the measurements, we come up with the first two very basic and very important data sets are, first of all, during drilling. This is borehole length on the x-axis, and on the y-axis is flow, which is measured along the borehole as it is being drilled. So the more you drilled, the more water you collect. So you have a continuously increasing, a cumulative effect. Then later on, what we do is the flow logging, where we use a flow logging probe and measure the flow into the rock or out of the rock, and calculate each fractures, almost each fracture's transmissivity, each flow and transmissivity. And this is done by moving the resolution is 10 centimeters. So if we have fractures that are closer than 10 centimeters, we cannot sort them out. It is as if they were one, but that's as good as we get basically. That is the individual fractures, flows and transmissivities. And parallel to that, we measure the fractures the fracture geometries, that is, the direction and the inclination of them. And then we plot them in this type of stereo plots of different kind to see how they are trending. So this is an example. Let's take this one, for example. We select all the open fractures. Okay, from 0 to 50 meters, this is what it looks like. So this type of plot shows that basically all open fractures are trending northwest, southeast. Okay. The sealed fractures have a higher horizontal component, but in terms of water, it's the open ones which we are interested in and which we want to correlate to the fracture inflow. So by seeing this picture here and seeing those fracture flows, we can fairly confidently say that, okay, that these ones, at least the major ones here, when we look close at them, it's water coming from northwest, southeast trending fractures. And this is important to establish the concept, the model later on. So inflow predictions, with this data, a first model was produced. Okay, these are fracture planes and deformation zone planes at the target area. So the major issues here were the high groundwater pressure and selective grouting or curtain grouting. This means to accommodate that we should not grout certain tunnels. The decision should be, how should we grout basically? So the first model was an input to that end. So the conceptualization here was, for the modeling, was that we have a tunnel here, which have a 0 atmospheric pressure. We have an impermeable base. We have a certain initial groundwater level or pressure level. Okay, when we introduce the tunnel, we have a drain and the pressure goes down. So with this as an input, we put in these fractures, okay, at certain distances, geometrically, basically as I showed you before. And then we started to do the calculations. But the other thing which is needed for the calculation is what we call the initial condition, the input parameters. So we have input parameters on the geometry, on the tunnel, on the rock properties, and on the fracture properties for the two main tunnels, which is called TOS P and TOS U tunnels. So that is the input, okay. Then when we process it through the calculations we did for different scenarios, the important thing here was actually the grouting. So if we grout, the conductivity goes down, of course. And we call this, this was simulated with a skin effect. So we applied to the fracture or in the fracturing of the deformation, we said, okay, if we add, you know, a skin which is restrictive to inflow, how does it affect the flow into the tunnel? So we applied the skin to the rock as such and to the fractures as such, okay, which are cross-cutting the tunnel. And this is the skin barrier, this is rock. So we have for skin 0 and 33, and for the LMDZ is local minor deformation zones. This is the fractures, basically, the major fractures which are cross-cutting the tunnels. So for different combinations here and for different drawdowns, for respective tunnels, we get different flows. Okay, so this was before they did any grouting or anything. We didn't know what the constructors wanted to do, just to give them an idea, and then they took a decision based on this. So then they went ahead drilling, constructed drilling and blast with the Jumbo from Sandvik, did the job. Now, the grouting is an important component in this. And the initial grouting, which is also the first question which they're asking us, the hydrogeologists, is, you know, what is the potential for us to not to do the grouting? These green holes, these green lines are representing probe holes. This is standard methodology when you build a tunnel, that before you start blasting, you drill some holes, you know, just outside of the periphery of a tunnel, of an intended tunnel. And then measure the flow and what happens, just to get an idea what you will encounter. You don't want to get big surprises in terms of weak rock or large water flows. It's costly and it's dangerous. So that's why they do this, this type. And based on this, we can make a comparison of what since we drilled a pilot hole along the axis of the intended tunnel, we could compare it to the outcome of these probe holes, the curtain holes, to see. So the initial hole, the pilot hole, was drilled here in the center. So these probe holes, which are drilled on the exterior of a tunnel periphery, they are around 15 to 20 meters long. It varies, 16, 17 sometimes. But so for that length, along the tunnel axis, it represents this here, from 0 to 20 basically. Okay, so when we did the pilot hole, it showed no flow, or very, very little flow. When we drilled, it was basically 0, when we drilled the hole. When we made the flow measurements with the flow log, there were some flows, but they were so low, so we didn't pick them up in the drilling. So that is the result for this length of a tunnel, which the pilot hole showed. Now, for the same length, for the 5 different probe holes, we obtained very different results. So these are in liter per minute. So we have 0 here, and we have up to 92. So this is a very heterogeneous system, and that's why we need to characterize it a lot to understand it. And the construction went on. Okay, so drilling and blasting, feedback from the information, and then updating the models. So we went from the beginning, the M1 model, which I mentioned previously, and on which we made predictions of inflows, until the final model 2.5. So on this model, the layout, the final model and final layout. So more or less, we obtained this picture here, but I mean, there is an alteration here, of course. I'm not going into the details. And the implications of a modeling were 3. It's this on top here. So this, due to modeling, we shortened the main tunnel and went sideways instead with different tunnels. That was one. The other implication of the modeling was that the shifted position of experimental tunnels. So these sideways tunnels, which are the experimental tunnels, from the initial layout which we had, I mean, we positioned them in consideration of the fracturing, the deformation zones, and the water transmissive properties. And the other one was also in the same spirit. Of course, we changed the orientation also, the position and the orientation. So the overall picture of the layout was the same, but they were shifted and moved a bit to accommodate it. And to summarize the inflow predictions, so as I mentioned, the predictions were made with different grouting effects. So so this is for the tunnel, the first tunnel and the other tunnel. So the prediction was that if we don't grout at all, the inflow would be around 70 in one tunnel, liter per minute, and around 60 in the other tunnel. So the decision was taken that we do not do selective grouting, we do curtain grouting. That is, the main tunnels are going to be grouted all the way, but not the side tunnel. That was selectively. So for the grouted case, okay, the prediction was that one tunnel we obtained around 40 liter a minute and the other 5 liter a minute if we grout it. If we grout it and we decrease the T over 100 means that if we decrease the permeability by 100 times, okay, then, because this was also an option, we get this. They actually measured. That was predicted that this is measured. And this is the actual time series of a measurement for 2 respective tunnels. So we obtained 5 liter per minute for the one tunnel to be compared to 15. Okay. And the other one, the actual inflow was 12 and we predicted 5. That was the result, basically, of the prediction. Just to have a check in the end. And the final modeling layout is as follows: that we found high groundwater pressure. This was particularly important for one project, which was absolutely adamant that we must have high pressures, otherwise we can't go ahead with the project. So we found it here, and it's still valid. And they are going to do an experiment. They have started. The other one, we found 3 places for 3 tunnels for round grouted. This is the white tunnels here, basically. And the other tunnels here, they are grouted, of course. So, to conclude, we were able to deliver, high groundwater pressure and suitable and areas where no grouting was performed. Thank you very much. Questions?